Mauricio is our fourth speaker. He's filling in for Dr. Branko. Glisic. Mauricio.
Hello.
How are you?
Good, and you? How are you? Yeah, hello everyone. So, I said I'm Mauricio, and I'm presenting on behalf of my friend Vivek Kumar, who was with our group till last year. So, I'll be presenting their work on I'll be presenting their work on a sensing sheet for damage detection over large surfaces of structures. So, as we saw, the main motivations are cracks, because cracks can reduce the structural safety and reduce high maintenance costs in our structures. So what we'd like to have is a reliable crack detection, localization, quantification method. In our approach, we are looking into strain-based SHM. And the idea here is that significant changes to the structure will cause changes in the strain field that we can measure. So one initial approach there would be, for example, for us to measure strain at a particular point. So you could have point strength sensors, such as resistive strain gauges. But those, of course, will have limited spatial resolution because they have very large surface areas, very large volumes. So one natural extension of that would then to have linear or 1D strain sensors. We can achieve this, for example, by using fiber optic strength sensors, something we use a lot in our group. While those improve your spatial resolution, they can be costly to scale, especially if you want to cover surfaces or volumes. So the next step then would be to consider area or 2D sense sensors that are scalable both in size and in cost, right? So that's the idea of this project. So we developed what we call a sensing sheet. And the idea here is that you have what I would call a unit. So imagine this as a regular resistive strain gauge. And in particular, we assemble them in a whetstone circuit so that we minimize thermal interference. And that this bundle of 4 units is what I would call my sensor. And I imagine that you put all of these in an array. So basically, each one of these blocks, can you see my mouse? Each one of these blocks here are 4 of these units consisting of a sensor. And now basically I form a dense array of those. And here I can throw all sorts of types of controls. So for example, I don't need to read all sensors at once, right? I can have a scanning process here that allows this to be energy efficient. I can embed computing right at the sensor, so I can introduce some simplified algorithms there to minimize energy. So I can deploy this for very long times, even though it's based on resistive sensing. And here I show a sample of the sensing sheet that was manufactured for us to test at the lab. And this uses standard manufacturing methods for circuits, with the difference here being that those are printed on thin film flexible sheets so that you can basically mold them to your structure. And in this particular sample here, I have about 20 by 8 centimeters, but this particular manufacturer can make them as large as 30 by 30 centimeters. And essentially they have 3 layers, the polyimide, an adhesive, and constantan, which is our resistive material there. This is our sensing material. So initially what we perform laboratory calibration of the sensor. So the first thing here is, does this work and how does it compare to a standard commercial sensor? So we have an aluminum beam at the lab, which is encastered on one end, and we can control its deflection at the other end. And basically here we'll be comparing the sensing sheet readings with a commercial sensor in a static setting, so basically varying stepwise. And we can see that for static measurements, we have very good agreement between the commercial and the sensing sheet. And then we also have a dynamic setup in which you compare the sensing sheet readings with fiber optics reading. And the red one here represents the fiber optics, and I think it's showing green, okay. It's showing black for some reason. And the green represents the sensing sheet. You see some phase, but the peaks are actually in quite good agreement. And if you compute the power spectrum, you see that they show very good agreement. So the point here is to show that by using the sensing sheet, which was manufactured just by sending this design to a regular commercial manufacturer, you can achieve equivalent measurements based from other commercial sensors. But then now the question is, can the sensing sheet be used first to detect cracks? Because that was the whole motivation. Can we use to localize the crack? And can we somehow quantify the crack, for example? Can we know how much this crack opened over time, or how does it change over time? So let's address initially the detection part. So for the detection assessment, we propose a second laboratory setup. So what we have here are two aluminum plates with a gap that we can control using a micrometer. So we have very fine-grained control of that gap. And the idea is that we'll increase this gap stepwise and see if we can capture this in the with the sensing sheets. And then we consider two setups. One setup here is what I'm going to say is the sensing sheet is aligned with the crack, and one in which the sensing sheet is inclined with respect to the crack. But you have to think that what is changing is the length of your resistive element in the circuit. So for each bundle of these, parts of the resistors are over the crack, and part of the resistors are not in the crack. But from all these four, you get just one number, right? Just one voltage. So it's not trivial that you should be able to detect them easily. And if you look here on the plot, the sensors 5, 6, 7, and 8, which are the ones covering the crack, they show very large amplitudes because you're measuring a displacement, a strain comparable to a crack strain. Whereas the other ones that are far away from the crack are not shown here, but their magnitude is an order less. And similarly for the inclined case. So the point here is that even if I apply very small displacements, I can pick it up. And because now I have a sensor that covers an area, part of this will be over a crack, and it becomes obvious. The crack is there. The signal is very high. So my friend proposed a method here to detect this by computing the strain rate over time. So if I compute the strain rate over time, what I will get are those peaks, right? So as I apply the steps, the strain rate increases a lot, and I can capture this, and I know that a crack is occurring. And if you think about this in the real-life setting, you would see an increasing slope versus no crack there, especially if changes in thermal. And then one interesting aspect also is that the ratio between, so if you consider the strain measurements from all the sensing sheet and you normalize by the highest strain that you have, those ones that have a crack crossing them show this constant response once the crack has started. So that could be an indicator, okay, a crack has occurred, I can detect it. So that's the whole point, I can detect this crack. And likewise, for the inclined case, so again, I can use the strain rates to figure out the growth of the crack, but then I have these constant ratios after the crack has appeared that show me that the crack is present under that particular sensor. So now if I look, for example, on the top plot here, I'm seeing sensors 8, 7, 6, and 5, but I know where they are in my sensor area. So basically, I have localized the crack. I know there is a crack crossing all these sensors. So likewise for the inclined case, so here I have the strongest signals, for example, on sensors 1, 7, and 8, and a little bit on 2 here, although it's not appearing as strong here. So this gives us an initial guess of where our crack is. So now we're into crack localization. So basically, we show that with the sensing sheet, you can detect the crack, and you can also estimate the localization since you have sensors that are on top of it. I'm not going to go into the details of the analytical approach here, but you could further improve your estimates of where the crack path is by considering a baseline case in which the crack is crossing some of your resistive units, and any other case in which the crack is inclined or crossing other sensors and so on. And if you compute the strain ratio between those two base cases, you get an index. And then when you perform your measurements, you have your measure indices, and then you can compute analytically what these indices should be, and you can make them match. And by making them match, you improve your guess of where the crack is. That's the idea here. So basically, you can use an analytical approach to improve the crack estimation. This can be done automatically. And then the next step is to show the field application of the sensing sheet. So one first step here is to see how the sensing sheet performs compared to standard sensors. At Princeton University, we have Streicker Bridge, which is a bridge instrumented with fiber optic sensors at multiple positions. We installed the sensing sheet at the bottom of one of the cross sections, where we also have two fiber optic sensors, one at the top and one at the bottom. And we compare the fiber optic strain measurements with the sensing sheet strain measurements over a period of 5 hours. And here you show the setup where basically the sensing sheet is glued to the bottom of the bridge, and you have the transmission and the readout setup on the bottom. So all the colored points you have here are basically each one of the sensors in the sensing sheet. We have 8 of them, and the dark dots are the fiber optic reference. So you can see they show fairly good agreement, and the point here is to detect cracks, so you don't need very high agreement between them, and also consider they're not exactly at the same point in the cross section. But this is sufficient, for example, for one to detect the crack there. And then on a second field application, we applied the sensing sheet atop of what we think is a shrinkage crack on one of the supports. And we did it in such a way that part of the crack is crossing some of these string sensors, and part are outside of the sensor. So you see that the ones that are not on top of the crack show a very, very small response, whereas the ones that are on the crack show extremely larger response. And not only that, so basically what you have here is the structure. So this was over a period, let's say, 12 hours. So what you have here is a changing temperature. So as the support is expanding, the crack is closing, and vice versa. So that's why you measure this opening and closing of the crack. And because you have now a strain measurement, you can measure how much it is opening, how much it is closing. So I think it was way faster than I was expecting, but so what we presented was a thin film dense array sensing sheet that is fairly scalable both in manufacturing. It's also energy efficient. For example, the test that we showed there runs for 5 hours, but if you sample every minute, you can go several days, for example. We demonstrated on static and dynamic laboratory testing that one can perform crack detection and localization by covering larger areas, and also perform field tests, which you compare it to standard fiber optic sensors, and that we can quantify the crack opening. So thank you for your attention, and if you have any questions.